All right, so it's my great honor to be the 300th kind of a colloquial speaker at JQI. And as Paul said, I know we know each other all the way back since I was a student. That's more than 20 years ago. And Paul looked exactly the same as 20 years ago. I so very energetic. We had all the kind of exciting discussion for many years. Okay, it was a great connection with this NIS, JQI, and so on. Okay, so many other colleagues like Charles Clark, and this Trey Portal that we have a kind of recent discussion on this super resolution imaging and so on. Okay, so today I'm also honored to be the first speaker in the kind of this in the fourth semester. Okay, I'm hoping to share with you some of the exciting kind of result from our lab, which is unexpected. Okay, so as you might know, in the experiment sometimes sometimes you have very specific goal. There's certain phenomena being predicted for decades. I just want to see that. Okay, and sometimes you want to have an engineering goal. There's with a new technology, I can understand the phenomena better. I have a very specific goal. But this is a very different type of kind of experiment I'm going to share with you. The unexpected quantum phenomena coming from the condensate. All right, so my name is Cheng. I'm from this Department of Physics at the University of Chicago. Okay, and was supported by these funding agencies. Yeah. Okay, hope you can also see my laser pointer. All right, so let me see, move on to the next slide. Okay, no. Yeah. Let's see, page down. No. Just let me see next. Okay, and a few words, and also this we recent at the University of Chicago with a recent recruited data mill. Okay, so at the moment we start building our AMO group. This I'm mostly working on atoms, and John Simon have been joining us for like about I think maybe 8 years. Okay, more working on photons. So happy to have Dave to join us. So really complete the circle. A for atoms, M for molecules, and O for optical physics.
Okay. That's great news. I hadn't heard that. Did he? Right. He just came on board.
Yeah, we work on his case for essentially 2 years. Okay, this is especially also in this difficult time. It took a while to really convince it higher up, but we think we're now in great shape. Okay, this three of us can work together. All right, so let me start a story by this short email from my student. That's in 2017. You can see right here in March 2017. So it's a bit more than a bit more than 3 years ago. So I remember I was preparing my lecture. I was teaching electronics. Okay, you know, a lot of details and so on. Prepare the lab and so on. I was pretty busy. And then turns out my student Logan Clark, Fonley, and also postdoc Anita from Poland. Logan is a US student, and Fonley is from China. So it's a great team working together with the talent from all over the world. And then they sent me this short email. They have been hiding something from me. They know I'm busy. I don't have too much time. They say I have a secret project. Just wait for another week. They want to figure out what's going on. And this is the email that really reveal their secret project. Okay. All right. So what did they say? So in Logan's report, okay, this is in the same email. This the page 1 of the report. So he said at the end of last week, while attempting to work on generating dynamical gauge fields, we made a rather fortuitous and a beautiful observation of what we are now calling Bose fireworks. None of us had any idea what happened to these atoms. Okay, we tried to explore some other phenomena, but then you can see as a function of time. Okay, these are 3 independent runs. We just see this atom shooting out of the condensate with this very thin kind of needle shape, okay, like a thin jets of this something, okay. And then, so you see this structure, okay, and if you repeat the experiment, every single experiment show a different structure. And the condensate also left in some kind of weird state with all this kind of structure inside and also outside this condensate. For the next couple of months, we know there's something that is reproducible with this strange pattern. And some of them you can see this, the needles are seem to be pointing in opposite directions. Okay. But some are not so clear. And it was a great exploration. Okay. And this is what eventually put on the paper. Okay. This without too much, you can see there seems to be some kind of ring in the middle. And then this needle-like emission, now we call Bose fireworks. Okay. Essentially started our exploration into this weird, unexpected phenomena. So now 3 years or more than 3 years after our observation, I feel like what we've been doing in the past 3 years is like an exploration in a totally new world. Okay, and what I have this photo is called the land of Pandora from the film Avatar. So you come to this new world and look at that. What is that in the sky? Is that a mushroom? Okay. Is that maybe that's a jellyfish? Okay. So you see something you've never seen before and try to make connection to something you are familiar with. Okay. But you are not quite sure whether this is, maybe it's an octopus. Okay. Who knows? Okay. And we feel like we're kind of enter this new wonderland and we need time. Just imagine if you are zoologists or botanists and going into this new garden. Okay, there's so much to explore. All right. So first of all, what's a recipe to create this the fireworks? Okay. So here, there's 2 simple steps. One is that this I think this is to create a condensate in a very thin and this shape kind of optical trap. So where the green beam to define the wall and the red beam to provide a vertical confinement. Okay. And then the condensate is confined inside this dipole trap. The thickness about 0.5 micron and the radius is about 20-30 micron. I think similar kind of setup also been worked on, okay, at JQI for many years. Okay. So it's a circular shape. And this is a regular BEC here, cesium, but the scattering is small and is a fairly regular BEC to begin with. Step 2, we use a phase power resonance. That's something I learned a great deal from this Paul Julian. Okay, this how to control atomic interaction. Okay, and here for the first time we are ambitious in the kind of this break enough to try to modulate atomic interaction. So there's an ADC. ADC means a kind of a nominal value before the modulation, which is only like 10 Bohr and so on. And AAC is the amplitude of the modulation, okay, all converted into the units of scattering length. And then there's a 1/f, that's a frequency of our modulation. And finally, the tau is how long we perform the modulation. So essentially, they are only like kind of this few parameters in this case. Okay, to characterize the modulation, the amplitude, the frequency, and the time. Okay, ADC turns out to be not important. After the modulation, we perform the in situ image on the system. That's it. So, and what I show you is the top view. We have a camera on top of the disk, so you can see how the particle, how the kind of these particle leave the condensate in terms of this jet structure. Okay, form this kind of jets leaving the condensate. We also had a camera on the side. So more like this looking at the system, if you can see me, okay, from the side of the disk. And then you can see the emission is mostly on the XY plane. Okay, there's almost nothing going on in Z direction. So that first, that shows that there's a very anisotropic emission. Just to remind you, at that time we still had no idea what's really happening here. Okay, all right. And then immediately one thing we try to compare the particle leaving the condensate as a function of time. So what this particle leaving the condensate, this in principle should carry some energy out of the condensate. We know condensate has almost this negligible kinetic energy. So these particles seem to be energetic. So we try to measure the kinetic energy. To our surprise, this is really to our surprise, because quite frankly, we thought the kinetic energy of the excitation should be the same as the modulation energy. say if the modulation frequency is 5 kilohertz, well, obviously we really kind of expect to be 5, but then it turns out to be 2.5. Okay, so you see there's a very linear relation, but it turns out the slope is 1/2. For some time, we thought perhaps we are exciting two atoms together. Two atoms share kind of share the h bar omega. Okay, that's a thing about photoelectric effect. But then how is it possible this kind of two particles go in the same direction? And later we realized when you look more closely into this emission, you can see some of these show a very clear kind of correlation. The particle going to one side is also accompanied with the particle going to the other side. Okay, some of them are clear, some of them not too clear. So here you see this is not so symmetric, so shorter time. So you see, well, there's a factor 2. Okay, likely there's some kind of a two particles being excited together. That's why each particle shares half the energy quantum.
Cheng, is this the
yes.
images you're showing? Is there a maybe I missed it? There's a time of pre-expansion of the cloud.
No. So
could you just show the timing of the pulse sequence again? I'm sorry, I missed that.
Okay. So our potential is remain kind of stationary. So we don't know the potential. However, when you do the excitation, these particles have high enough energy to go through the green wall.
Okay.
So, but for the remaining particle, they the remaining BEC remain trapped inside the green kind of.
So we're just seeing the time after the modulation of the potential started.
Yes. So
and it's continuing indefinitely.
Yes. Okay. The tau here is exactly the tau showing this the time we perform the modulation. We perform the modulation for say 5 milliseconds, then we perform the imaging immediately after that. Okay. So no modulation, 6 milliseconds, and 10 milliseconds. So after 24 millisecond modulation, then we see something leaving the condensate, and there's a kind of a wave kind of leaving the condensate. Okay. Afterward, this is also getting pretty weak. All right. So energy-wise, that is the first indication. Okay. And second, how about amplitude? It turns out we need to really perform the modulation large enough amplitude. Our ADs are nominal scattering lengths, typically about 10 Bohr and so on. Our modulation amplitude need to be plus 20 to minus 20, so in this case, or plus 30 to minus 30 in order to see the emission. So before that, there's some kind of weak kind of excitation. Okay, that doesn't quite lead to the fireworking. Okay, but firework pattern is more obvious when you have modulation amplitude exceeds some kind of threshold. There is there is a threshold. Okay, you need to go beyond the threshold to see the clear emission. But the most fascinating thing for us is how do we characterize, why do they form these very thin needles? Okay, these needles have a width that's smaller than the size of the BEC. Okay, and then there are so many of them, but it also seems to be quite uniform. It looks like this each needle has a particular kind of width. So that took us the longest time to figure out how to characterize the structure. Okay, but so eventually, what works for us? Okay, what we do is that we try to only look at the signal in this ring area. So we block the BEC and block the background, and then try to see what is the density distribution as a function of angle. In particular, we found that it's particularly useful to look at the correlation between the particle emitted along the direction at theta and theta plus phi. Okay. Essentially, one want to see whether there is some kind of correlation when the two emissions are separated by angle phi. Okay. So you might know this, I can define a correlation function. Okay. Essentially look at the product of the particle number within this slice and the other slice. You multiply them together, and then you average over theta. So you average over all possible thetas, but keeping the phi constant to look for whether there's any correlation between any two particular directions. So that helps. That helps us, and the result is very interesting. When you change the phi from small angles down to almost 0, all the way to 180 degrees. 180 degrees meaning trying to look for the correlation between particles going in the forward direction and backward direction. And then for different amount of time, we see very similar kind of this result. Okay, there's some kind of background value 1, and when phi, when the relative angle approaches 0, then we see a very narrow peak. Okay. And this peak is so well can reproduce, we can define the width. Okay. Now we start to call this is the width of a jet. Essentially, when the angle is small compared to the width of the jet, essentially emissions are happens together within one jet. All the particle will come out within the same jet. So that we can define, in this case, just the width of the jet about 3 degrees. So there's strong correlation within 3 degrees. When go up to say about 10 degrees, you no longer see correlation. 1, it's been properly normalized, meaning there's a random emission. When you have random emission, that's been normalized to 1. Well, when you go to 180 degrees, it turns out there's another peak. So that's kind of confirm our visual kind of understanding that there seems to be some kind of correlation when particle going to the right is accompanying particle going to the left. However, our simple model with suggests it should be 100% correlation. And what's beyond the simple model? The simple model is just saying, in principle, there should be kind of a momentum conservation. If I see more particle going to the right by 1 atom, there should also be more particle going to the left by 1 atom, okay? Because you expect a conservation momentum. But what we see is a more shorter and also broadened peak, okay? It's a peak at 180 degrees, but it's not 100%. All right. And the other thing I would like to point out is that you can see this correlation doesn't seem to depends on time, at least from 4 to 8 milliseconds. Actually, we try to go over longer range for 4 to all the way to 60 milliseconds. So we can also see how many particles being emitted per 3 degrees. Because we use the 3 degrees to define the width of the jet, so we can define how many atoms per mode or per jet, okay, are coming out of this condensate. So from the measurements with the lowest kind of resolution, we can see about 10 atoms per mode. Okay, we can see that the population seems to be increasing exponentially in the first about 4 milliseconds before it saturates. Okay. And if you try to extrapolate the population all the way to the beginning when driving time equal to 0, it seems to go down to this level, about 1 particle per mode. Okay. But because it's a pair production, that turned out to be half a particle per mode. So that's consistent later with kind of our quantum model that the structure is likely coming from quantum fluctuation. So what that means is that if you look at this pattern, from our understanding, this structure is the quantum fluctuation being amplified by hundreds of, in this case, a few hundred times. So every time they look different because the fluctuation cannot be reproduced. In some direction is strong, some direction is very weak. So that is example. One direction is strong, one direction is weak. That's just the way it is. And we are looking at this, quite likely we are looking at quantum, just a quantum fluctuation in front of our eyes.
So that correlation function that you're showing,
yes,
is that taken for all the jets that we see or just some subset of them? I mean, I guess
average over, if you look at this expression, average over all theta.
Okay. Okay. All right. So it's a global G2 averaging over all
pairs.
Well, let's say you have 2 angles, theta and phi. So you
That's
fix
right.
theta, and then you look at the correlation function for the points in that jet as a function
right.
of phi.
That's
and
right.
then you, okay.
Then we average overall.
Average overall. I see.
Yes, right, yeah. Actually, for this column, we also average over multiple shots, okay, multiple images.
Yes, of course.
You average over all angles, all these possible pairs.
So we also have a question from the YouTube stream.
Sure.
which is there. So Amitabha Banerjee is asking, is the residual condensate at the center after the jets leave any different from the initial condensate?
Yes, the condensate also being excited. I will also tell you a bit more about what we learn about the condensate structure a bit later.
Okay, great, thank you.
All right. So by this time, we think we're enough. So we finished the first paper. And soon after we kind of published paper, we got contacted by unexpectedly by a particle physicist. So this Dr. Miguel Arratia is now professor at UC Riverside. He talked to us. He said, hey, what you have is very close to the kind of correlation people see in this high energy scattering experiment. Okay, so Dr. Arratia, he's working at CERN. Okay, and this is something that he's been working on for years. That's a look at the what people call the digest equilaterality. So when you start to have a look at the proton-proton collisions, it is very high energy. They also see jets of pions and so on. This high energy particle coming out of this dense sample, also in terms of jets. And then they also see this narrow peak when the relative phase is 0, and this broadened peak when relative phase is pi. Pi means 180 degrees. Okay. And in their community, is this jet structure plays an essential role to understand what is really going on within this short time in the dense sample, what they form this Coulomb plasma. So, and they start, because the jet is something they can see as a kind of show macroscopic population of this well, we call it bosons, like pions and so on. So that provides a good evidence for them to figure out whether these jets are created by gluon or by this what's the other particle, quark. Okay, all right. Eventually, he wrote this paper, try to compare them, and also use the language from particle physics to describe our system. But we realized there's a very, very big difference between our systems. Okay. However, what we learned from one experiment kind of side is that we learn about how these people analyze the jet structure. They certainly have a much longer history and a more developed expertise to identify possible correlations and patterns, okay, in in high energy emission, high energy experiments. So one thing my student learned, okay, this my former student, Hong I'm showing here because I think he's also in the audience. He's now working in Chris Monroe's group on ions. So he applies similar type of idea, say, we can also try to see whether there are other patterns, okay, using the so-called this pattern recognition. Okay. Our system has a kind of a simple symmetry, so we can use the symmetry trying to just help us to identify potential patterns. So he developed the so-called machine learning algorithm, okay, trying to identify whether there are other patterns that we do not see clearly, we do not see just from that kind of this simple correlation kind of experiment. Okay, I showed you earlier. For example, here, this is a few individual emission pattern from the condensate. We block the center, okay, because center is too bright. Okay, and then look at the emission on the ring. So you can see individually it's not quite clear. Well, some of them you can see there's a correlation and so on. But sometimes you also see some other stuff that we didn't see or didn't quite appreciate in our first paper. Okay, you see there's even another peak that's pretty strong here. So what they did is trying to see whether we can define some kind of a principal axis. Use a computer to define identify some kind of principal axis. Okay, and then orient all these patterns in the same direction. So you go back to the original kind of image. These are they all have a random principal axis. Okay. But now we just assign this rotational angle to each image, and then just send this whole thing to this computer, trying to orient all of them into the same direction. Okay, and try to see what kind of pattern we can see. Are there more structure we can see okay, from just the pi, the 180-degree correlation. All right, so made a long story short, it turns out he identified there's a pattern like a turtle. Okay, all right, I'm going to show you as an animation how they kind of iterate this process, okay, for based on 209 images. And what you show here, what I'm showing here is a direct averaging of 209 images without any rotation. Okay, and if I can do this, let me see how I'm going to set the. All right, good. I'm going to play the video. You can see under each iteration. Sorry. Computer trying to orient this image, 209 images, and try to identify principal axis and overlap them. Okay. So after 2,000 images, I think if they can correct me, it took about kind of 8 hours or overnight to get this whole thing to work. All right, so you see the turtle emerges. Okay. So here's the head and the tail, okay, and also 4 legs kind of growing out of the shell. Okay. All right, so that is quite unexpected. Also, for the first time we saw this, all these kind of final correlation. You can also see here's also another one, yet another one. Okay.
I think Alan Migdal once predicted this.
Oh, really? Okay.
Yes, he told me it's turtles all the way down.
That's quite unbelievable because that's what I'm going to show you about these turtles all the way down. I like to get the reference from you, Charles. Okay, so but getting the pattern is not the end of the story. So this what we as a physicist would like to understand from this observation, how do this pattern emerge? How to this whether we can have a better understanding what's going on. So let me show you this what Lei and I we kind of figured out this what lead to this correlation. Okay, what lead to these peaks. Okay. I like to mention this is in momentum space. So while you see this px, I need to get my laser pointer back. This pointer. Okay. So BC resides at the center with 0 momentum. Okay. And then the strong kind of a correlation 0 and a pi can be represented by these white dots. Okay. And that can be understood in the powering process. When you do the modulation, it turns out this is more like a parametric modulation, okay, excitation. You create particle in pairs. So mathematically, you lose 2 particles in the condensate, but condensate has a lot of particles, so you replace by C numbers. But then create 2 excitation, one is momentum K, and the other one must have a minus K to consider momentum, consider total momentum. So therefore, a pair production, K and minus K, okay, going in opposite direction. That is our kind of first order process. And then it turns out there are secondary collisions. What happens is now we look at the left-hand side carefully. You can start with 2 particles, one with 0 momentum from the condensate, the other one with a particle already with momentum K. And they can collide again. One move to the right, one move to the left. This process also conserves momentum, okay? But it turns out at the end, you have one particle with momentum K. The other particle momentum turns out to be square root of K, because the one step in the X direction, one step in the Y direction. Okay, so turns out momentum increase from K to root K. So that creates this the legs on the right side, and also explain the other 3 legs. So this turns out this secondary process explain the 4 legs of the turtle, as well as the 2 side peaks you can see here. Now, the last one to understand the head and the tail. Okay, again, that turns out to be 2 particles from here. Okay, both particles with momentum K, but now eliminate them. Create 1 particle going back to the condensate, and the other particle going to the 2K. Okay, again, for momentum conservation. Okay, for the sake of momentum conservation, the other one must go to 2 times the momentum, 2K. So now you can see all these, you can start to understand, you look at all these process. The first one is dominating because you have a knot. Okay, that's a large number. And this secondary jet is also pretty strong by proportional square root of knot. Okay, that turns out to be the higher order process. Okay, so here we get a kind of complete understanding of this the turtle pattern we see. Okay, and you can see more details and this and also the calculation in the science paper. Okay, and we also try to extend this calculation. What happened to even higher order? It turns out this process goes up crazily. If you consider tertiary jets, it will be more than 600 modes. So we now we know this is a good time to stop. All right. So just like what Chao just mentioned, we also being asked to give a more general comment how to understand this crazy pattern we see from the pattern recognition algorithm. So this is from our this Chicago news office. Okay. Get this out of the way. Okay. So yeah, they kind of fascinated by this pattern, but eventually there's one sentence that's been quoted. Okay, that with a larger font. In essence, each image consists of many such turtle patterns. So we identify the pattern, but original pattern turns out to be a superposition of all these different turtles, some stronger, some weaker, and each of them also orient in different directions. Okay. And what we see is just overlapping of this turtle different strength. Okay. And this is also kind of what we said is the turtles all the way down. All right. Okay, so at this point, okay, we kind of understand this. There are kind of higher order process and get to more structures. Okay, and you can also see this more from the theory kind of understanding. There's some kind of symmetry breaking. In the beginning, is the twofold symmetry. Once at the four legs, okay, it seems to have a kind of fourfold symmetry emerging from the secondary process. So now it came to this, so I understand this jet structure can be very complicated. And that's just something we're still working on in the past, afterwards. We still have two more papers trying to understand more structure. Sometimes we even see the emission, you can look very carefully. The emission even seems to have shown some kind of spiral pattern. That turns out happens when this, the BEC created with a vortex, with a positive angular momentum or negative angular momentum. So it's more like kind of sprinkler when it's kind of spinning. So you also see the kind of water being kind of spilled out with a kind of spiral pattern. Okay. And now we have a theory, the theories I will collaborate with my colleague, this Kathy Levin. She now has a pretty good code also to reproduce this pattern. And that might help this to associate the quantum state of the BEC to the emission structure. It's a J emission structure. Okay. All right. So at the same time, we also change our focus. Somebody asked, okay, so how about the kind of structure on the, within the BEC? Okay. And that coupled to another question. So whether we can really control the pattern we create. Okay. So in a very interesting discussion with kind of a soft matter kind of physicist in our department, Tom Wheaton, he had been working on this kind of pattern formation in kind of soft matter and even biological systems. So he said you should check out the so-called Faraday waves. Okay, Faraday waves. I'm going to show you the video in, very quickly. But then with the discussion with him, we realized, okay, in principle, we can also generate pattern with different symmetry going beyond fourfold. Okay, I'm going to first show you this. Hope I can show. Okay, very good. Can show that this is a Faraday wave. So what's a Faraday wave? Just one example. You have a thin dish of water, and then you try to shake it. For example, you can put it on top of a speaker, and then you can tune the frequency of the speaker, okay, the frequency of the sound, okay, and so you shake the water vertically, but you're looking for pattern on the horizontal plane. So the pattern must come from some kind of a symmetry breaking. In the classical system, maybe just imperfection or kind of some more fluctuation. Okay, but you can see it's pretty obvious here. So it's in the beginning, they tune the frequency, some particular frequency, then you see this, say, the square wave pattern emerging on the surface of the water. Okay. And for other frequency, then the pattern can disappear, or some other symmetry can also be created. When the pattern is formed, even the system can be very stable, okay, to withstand kind of strong perturbation. Okay, see, it comes back. All right. So whether we can also create something like this in the quantum system, now it was fascinating for us. Okay, and so here I try to show this our theoretical understanding. Okay, so we no longer use a classical wave equation. We need to go to for quantum gas. We need to use use second quantization formalism to understand this driven condensate. So the most important term in our system is the interaction, and you know that proportional density square. Now the interaction is oscillating with time. So in principle, there are 4 operators because we have a wave function to the 4th power. But now there is the momentum conservation, which is called phase matching condition, say in quantum optics or nonlinear optics. There's also energy conservation, but energy conservation now is being supplemented with this energy coming from the kind of driving field, h bar omega. Okay. So if you put in this condition, now you can try to do the expansion order by order, assuming you start with 0 temperature BEC with lots of particles. Turns out to the leading order is this parametric amplification and kind of similar to parametric down conversion in quantum optics or in nonlinear optics that lead to spontaneous symmetry breaking. So that's the process, as we mentioned, you can create particle in pairs, okay? And that term proportional to BEC particle number. That's the first order process. You have 2 operators. You need at least 2 operators with finite momentum to satisfy the momentum conservation in this case. The next order, okay, you want to include, now the next order is 3 operators, okay, but momentum conservation should still be satisfied. So what you see here is I create particle with momentum K1, create particle momentum K2, but then you are losing particle with momentum K1 plus K2. So this process is also called nonlinear wave mixing. You think about here, one wave with wavelength lambda 1, another wave wavelength lambda 2, and when they collide, somehow they disappear and create this the 3rd wave, okay, with this wave with wave number K1 plus K2, or the reverse process, the Hermitian conjugate. So that can be kind of shown in the more complicated, kind of nasty kind of this dispersion. Okay, how the particles are created, create higher order modes. If you put all these together, you can write down the kind of quantum nonlinear amplitude equation is the analog of the nonlinear amplitude equation people use to describe Faraday waves. Okay, there you just replace everything by kind of this classical amplitude. But here we need to use this operator. It turns out there's one more term in the classical wave. The last 2 terms are essentially identical. All right. So armed with this equation, so with this the new generation student that try to analyze this equation theoretically, and also try ideas under this under condensate, try to see whether we can create more interesting patterns, okay, from the system. So this is the modulation we came up with. So we first perform some kind of single frequency modulation, okay, and that would create this pair production kind of. And then after 20 milliseconds, we switch to this more complicated waveform. Okay, look at more carefully. This includes several kind of frequency. There are 2 frequency components in the modulation. So you see in the beginning, t equal to 0. Okay, with a uniform BEC in the circular trap. 22.6 milliseconds right here. After the first phase modulation, we start to see some kind of stripes. And then after the second phase modulation, after 45 milliseconds, we start to see this lattice structure, okay, in a way similar to the Faraday waves. Okay, and this so far is all within the condensate. So how do we know what kind of symmetry, what kind of structure we have here? The simplest approach is that we can do Fourier analysis. To perform the Fourier transform, in the beginning, you see no clear structure. 22.6 milliseconds, you see create a momentum K and a minus K. This I should say, I should mention this is the Fourier transform the density distribution. But after 45 milliseconds, we start to have one, you can see 6 peaks. Okay, and this, by the way, this is based on single image. If you average over multiple shots, okay, then the structure can be averaged away. Okay, so this is momentum space. Okay, but now, because the layer earlier showed this pattern recognition, so this the new generation student also try to do this, but this time in real space. Turns out much more difficult. What we had to do is that every time we see this kind of pattern, similar to what I show here, the pattern 45 milliseconds. Okay, if we try to perform any averaging, okay, then the pattern will disappear. What we had to do is trying to identify there's some kind of principal axis, some kind of axis in this along the pattern. Okay, so you see each image has different axes. We first perform some kind of rotation to orient the principal axis in the same direction.
Could I ask a question about that, Cheng?
Yes.
In reference to the slide just before this one.
Yes.
So down on the center figure on the lower frame, has
yes.
that's as seen, right?
Yeah.
And then the next one on to its right, has that been reoriented to get the two momentum peaks in the same place?
These two runs are independent. So after 20.6 milliseconds, our imaging destructive. So this one is based on a new kind of experiment. But this
yes, I know. But are the direction has that image been? Has there been reorientation of these images in the lower row so that you get this common axis that's going
No, I think that seems to be a coincidence. Okay, it's just these two seem to be in the same direction.
I see.
It should have no correlation.
Okay.
All right. Okay, so we create this pattern, but just like we show in the classical Faraday wave. So every time the orientation might change. So you want to enhance the signal to noise. What we had to do is that we orient this individual shot such that they all point in the same direction. Okay, and then the second step, we need to translate. Okay, such an overlap valley with valley, peaks with peaks. Okay, otherwise valley with peak, and then eventually it will also disappear. So we do the translation, so you can see we translate this image in X direction, Y direction. So for each image, there are 3 independent variables: orientation and also the translation on the XY plane. And then we do the averaging. Okay, so this takes a much longer time because there are multiple there are more variables, okay, associated with each image. At the end of the day, okay, we show that if you only do modulation in single frequency, we see the stripes, mostly the stripes. There are a little bit some other stuff. But when we do this more the scheme number 2, which I just showed you earlier, okay, we see the kind of this triangular pattern. Okay, now we draw some line to help you to see indeed there's some kind of triangular pattern being formed, okay, in real space. There's some other scheme. Okay, we also develop want to kind of amplify the D4 pattern, four-fold symmetric pattern. Okay, then you can see we draw the line, you can see the more like square waves. All right, so this is kind of this topic remains interesting to us. Want to see what are other kind of more interesting structure we can create if you do the modulation in some new ways. But our current understanding is that you need to have the first symmetry breaking, and then use a nonlinear wave process to induce a symmetry formation. Okay, it's also spontaneous, okay, symmetry formation in the second process. All right, now talking to yet another kind of this colleague of ours, okay, Bob Wu, who is a gravitational work on gravitational physics. This is really unexpected in the sense that it's kind of it's totally kind of out of our kind of radar for some time until this my former postdoc, okay, Zhao Zhonghu, and somehow initiate this discussion. Maybe there's another way to understand this the emission pattern using this to connect our fireworks to the so-called Unruh thermal radiation. First, I try to explain what Unruh thermal radiation. If you consider there's a vacuum, but this vacuum is not a classical vacuum, it's a quantum vacuum, meaning in principle, particle can be created virtually. A vacuum in my frame might not be the same as a vacuum in your frame if it turns out there is a relative acceleration. In the inertial frame, then will be the same. But once you move to a non-inertial frame, for example, the simply non-inertial frame will be a frame that's accelerating. Okay, so when you go to accelerating kind of a coordinate, you can also introduce some kind of an operator that converts the quantum state in one frame to another state. Okay, and that operation is called renderer operation. It's a unitary operation. You just change the basis. Okay, and but what happens if you apply this render operation? Now A is a parameter given the whole lot of acceleration you have. It turns out what you get is some kind of thermal state. And this is totally bizarre because you have a vacuum state which is a pure state to begin with. And then you only do a kind of frame transformation, okay, which shouldn't change anything. However, what you get is a thermal state. I use this figure on the left to kind of illustrate this idea. It turns out if you have any local observer on one side, okay, you see you can measure the temperature. It cannot be distinguished from a kind of a thermal state. But it turns out there's the same thing happening on the other side. Okay, so this quotation mark means it's an effective thermal state, but it's a correlated thermal state. And once it's a thermal state, you can assign a temperature. This is called Unruh temperature. Okay, and this you see acceleration one parameter here. In particular, if you plug in the number, you see because H bar is very small, C is very large, but in the denominator, turns out you need to have very, very huge acceleration to even create a weak kind of emission, okay, with thermal emission. All right, and this will make it very difficult to kind of verify in the lab. Okay, it's difficult to create such kind of higher acceleration. So how is any of this kind of related to our firework experiment? Okay, all right, we have a vacuum. What do you mean vacuum? We have vacuum meaning we have vacuum, the BEC without any excitation. If you forget about the BEC, only look at excitation, okay, then in the beginning, we had no excitation. That's why we define as a vacuum. Okay, and what we can do, we can evolve the system by performing this modulation. And it turns out, if we can perform the modulation in the way that create the Hamiltonian of this form, then the evolution operator, just by plugging in Hamiltonian into this expression, we know evolution operator is can be written this way, will be the same as a renderer operator. Okay, so in a way, we're trying to simulate frame transformation without going to the accelerating frame, but we'll try to evolve the system in a way such that the system been kind of converted into a vacuum system in the accelerating frame. Okay, so mathematically, you can show that these two operators are identical, as long as you have proper coupling constant to create this excitation K minus K. And this kind of pair production is exactly what we could create in the experiment. And my former postdoc is Jiao Zhong, who did a calculation, show the equivalence. And then the result is that if you wish to create any acceleration A, we don't need to go to any accelerating frame anymore, but we just need to provide a proper modulation frequency, proper coupling constant, and as long as satisfy this condition, okay, this relationship, then these two operators will be identical. So another way to look at this emission is that we are actually boosting the BEC into higher accelerating frame, and the emission is the thermal radiation we are supposed to see when the vacuum, okay, is being accelerated. Okay, so based on this identity. Okay, so with this understanding, I just show a brief proof. Okay, so this creation operator. Okay, this is a coupling constant for our Hamiltonian. Okay, then we can kind of solve it. Okay, with the approximation, we can solve it and determine the state of the system after some evolution time, and show that indeed the result, with the amplitude that has a thermal population. Okay, but then this n is a particle number kind of Fock state basis. Okay, and by the n and n, that means particle going to the right with n particle, but going to the left also n particle. But I need to sum over all n's. Okay. When you know the wave function, what we can measure is the population for this one k and minus k. Now there will be contribution coming from spontaneous emission, okay, or some kind of initial population also be enhanced kind of exponentially. So this is on the quantum side. On this general relativity side, okay, I just briefly outline. Okay, you write down the metric in the Rinder space. Okay, you write down the transformation. Then you can write down the creation operator in one space and the creation operator in the other space and show how they are connected. Okay, when you know the operator connected due to different transformation, you can show that in the Minkowski space, when you prepare the vacuum, compared to the Rinder space, the vacuum in Rinder space, they are related by this expression, okay, and they are connected by this kind of thermal amplitude, okay, for each kind of so this thermal amplitude is something that we can create by our Hamiltonian, and that is a Rinder transformation. Okay, so experimentally it turns out to be a straightforward proof, which what we had to show is that the emission has a thermal distribution. So what you show here, t equal to 0, that's in the beginning, we have a kind of we can try to evaluate how many particles being emitted out of the condensate. In the beginning, it should be 0, okay, but with some kind of measurement uncertainty until about 10 to 15 atoms. But when you go to 3 millisecond modulation, 4 millisecond modulation, 6 millisecond modulation, you can see the distribution. That is a number of atoms per jet. Okay, indeed shifted to higher particle number. Yeah, more and more particles being emitted. However, the distribution follows thermal distribution. So coming back to this the 5-word image, what you see the fluctuation is nothing but the thermal fluctuation. Okay, it's nothing but thermal fluctuation. But that thermal fluctuation being created by this unitary evolution of the vacuum state. Okay. So, but here we can define the temperature of the emission and compare to Unruh's prediction. Even define the entropy of the emission compared to Unruh, compared to the prediction, and then we see a pretty good agreement. Okay, and then you can also see in this paper we perform further tests to show that this evolution should in principle be unitary. However, somehow it creates a kind of thermal distribution. Okay. To prove that this system is a unitary, we show the system at least can be partially reversible, and also emission is a coherent emission that we can see kind of interference effect. Okay, so this is a fascinating kind of a connection, connecting the thermal process to a kind of a thermal, the quantum process, a thermal process. And I should also mention Unruh radiation is also the foundation. It's also one way to understand Hawking radiation. Okay, if you just look at the local space-time, okay, near the event horizon. Okay, it's a simpler case of Hawking radiation. Okay, the last topic I'd like to mention, there's the kind of a new direction we're going into. Okay, so that is, as many of you know, this trying to bring molecule into quantum gas has been a very kind of has been a long-term goal in our community for kind of a few decades, and there are several recent progress. Say from Harvard Conquenese group, they were able to just capture 2 particles and form them and pair them into molecules. And very recently, during the first for the first time, okay, in June's group, they can associate this atom into molecules and bring them into degenerate Fermi gas. So you might see how it is related to fireworks. It has nothing to do with the fireworks. Okay, I'm going to show you in a moment. So, but let me just one more.
Sorry to interrupt 1 sec, Chen.
Yes.
We should probably wrap up in the next 5, probably at most 10 minutes, unfortunately.
Okay, I'll do that. Okay, so there's a kind of continuing effort, okay, in our community trying to bring the molecule lower temperature, right-hand side, and higher density. Okay, and it's sort of holy grail trying to bring the molecule into quantum degeneracy. Okay. All right. So, and with one example that excited kind of community very much about in 2004, people show that it can pair fermions into either Cooper pairs or molecular condensate, right? And this certainly kind of lead to a kind of major wave and try to attract a lot of people from condensed matter to look into the quantum gas in this strong coupling regime. But this also the bosonic version of it. What happens if these atoms are bosons? Okay. You also have two atoms that are bosons. It can be annihilated and create a molecule. But bosons, atoms are molecule, atoms are boson, molecule also bosons. Actually been predicted for atomic BEC, molecular BEC, there's a clear phase transition even at 0 temperature. Okay, this is a phase diagram been predicted way back in 2004. Okay, and if you look at this to some extent is similar to our firework kind of Hamiltonian, because the reverse process, you can also dissociate one molecule back to two atoms. Say your molecular BEC is zero momentum, when they've been dissociated, you will have to create two atoms with momentum K and minus K. It's similar to pair production. Okay. So actually, indeed, the same group of students now kind of just using this similar idea, say, well, perhaps we can also see pairing and unpairing in the kind of atomic condensate. All right, so let me just show how we do the experiment, the same experiment setup, starting with atomic BEC. Now, this time, in order to pair them into a particular molecular state, okay, we also use a phase bar resonance that we can kind of modulate the atomic interaction and so on. Okay, and the basic idea is that trying to pair them into one particular molecular state and to create a molecular condensate. So this project we discussed with Paul Julian, people have tried this in the past, and they are kind of seeing a lot of kind of heating and great loss of molecules and so on. So, and not being able to see the condensate. Okay. But with our more recent understanding, we know better about how to control the kind of stability of the molecules. All right, so here's our result. We start with, again, BEC in a uniform chart in this circular box. You can see the uniform density here. Now, this time, we try to perform a more delicate, more careful engineer kind of control magnetic field, ramping across a phase bar resonance. Immediately after that, we blow away all the atoms, and we see these molecules. Okay. So you may wonder how come there's a hole in the middle. Okay. That turns out the hole in the middle because there's a magnetic field curvature on the order of 1 Hertz. Okay, that's very, very weak magnetic field curvature. But our molecule is so cold, and this chemical potential is so low, we can even see the effect of 1 Hertz. Okay. And then in this geometry, we can perform this equational state measurement and show that the molecule turns out forms a 2-dimensional kind of superfluid. Okay, as a function of chemical potential, when chemical potential high enough, it enters the superfluid regime. And from here, we can determine the molecular scattering. The same experiment on the atom shows the same behavior. You can see the kind of phase transition. The molecule actually see that I consider it actually pretty obvious. Okay, now it switched to a different equational state. And also perform the third experiment trying to see how the molecule unpairs. Okay, in this crossover in the kind of near the phase bar resonance. Okay, so pairing, unpairing, okay, in the Bose gas is very different from the Fermi gas. And this image, in the beginning you have a molecule, but you don't really see them if you only image the atoms. After we ramp across the resonance, we can start to see atoms reappearing, okay, also in this ring structure, because that's how the molecules are distributed inside the trap. Okay, and eventually they've been excited, they get more energies. And we're also in the discussion with another theory, Golden Band, to think about pairing, unpairing in this bosonic superfluid, and how that might tell us about some of the interesting phenomena in nuclear physics. So I'd like to summarize. So you can see from our firework initial 2017, we didn't even understand much about what we're seeing. Now it actually brings out a series of new kind of projects, okay, connected to different fields. Okay, and that's along our kind of this research direction, trying to hopefully can address some of the long-lasting issues, okay, outside atomic physics. And to new students, I'd like to have this, try to encourage new students. There are a lot to explore. Sometimes you just keep your nose to the ground and try to see, perhaps there's really pointing into something very interesting. Maybe you need to try a couple of years. My experience, probably every 5-10 years, okay, you might have see something that totally unexpected. Okay, and then set for your imagination how what you see might connect to kind of a new world or something you're unfamiliar with. Okay, finally, my last slide trying to acknowledge this student, okay, my former student Feng Lei, have been working on this pattern formation, also earlier student Logan and so on, and current student Zheng Dongzhang and Kevin Yao, they've been working on pattern formation and this molecular condensate. Also other experiment on lithium cesium mixture, okay, and also quantum metal synthesizer trying to integrate optical lattice and this optical tweezers in a single experiment. Okay, thank you for your attention.
Thank you for the wonderful talk, Cheng. So I think now we want to sort of open up the floor to more questions and eventually transition over to our discussion hour. And so maybe I'll hand the controls over to Charles for this portion.
Yeah, so anyone please, if I could just say, first of all, I just found this such a moving and evocative talk, because these topics of matter wave amplification and coherent, and matter wave mixing and coherent amplification were addressed in some of the first important experiments in BECs done at NIST, and they continue to come up in JQI work. For example, Gretchen Campbell's modeling the expansion of the universe, and my own work on Hawking radiation just within the past few years. It's a really wonderful subject for us to see in new guys. Now I'll hand it over to anyone else who wants to speak up. Jay, are you, did you wish to ask a question?
Yeah, so Cheng, yeah, this is a wonderful story. So going back to that slide, comparing with Unruh radiation.
Okay.
Yeah, the plot, yeah, I guess this is good too, but more the comparing between theory and experiment. So actually, yeah.
This
the one, I think. Yeah, this one, right.
Okay.
So, so for this red line, oh, I see. So the question is the effective acceleration, like how well does it match between theory and experiment? And maybe let me get, the reason is, I'm asking is, so way back when I was a grad student in Berkeley, I mean, I was a theory student, but I collaborated with Dan Stamper-Kern on spinor condensates and domain formation there. We were hoping that the domain formation there was from quantum fluctuations, but eventually we concluded that the numbers didn't add up.
Okay.
So I'm wondering here, is there a way to compare this? And so there could be two sources of generating. So the fluctuations, the amplification is of course clear, but then what you're amplifying from could either be the quantum vacuum or some small waves on the BEC. And if there's a way for you to establish which one it is.
Right. So for this experiment, one detail is that our modulation frequency need to be much larger than the chemical potential and the KT. Okay. So in our BEC, this chemical potential KT, they're all about 5 to 10 nanokelvin. However, our modulation frequency is near half a microkelvin. So it's higher by a factor of about 50. Okay. So in this case, so you can imagine this, the thermal population is suppressed by e to the power of minus 50. So we're pretty sure the initial thermal fluctuation is negligible.
Oh, wonderful. Okay, yeah, thanks. Yeah, well, that's very encouraging.
We have a question from a student or a postdoc at this juncture, please.
You started this talk. Can you hear me?
Yeah, can hear you.
Oh. You started talk saying that you discovered these Bose fireworks while trying to generate the dynamic gauge field. How
Yes.
about the dynamic gauge field?
Right, that turns out to be the last project Logan took on. So eventually we also got that to work, but it's more complicated. I didn't mention it. So what we had to do is combine the lattice modulation with the interaction modulation. Okay, so we were able to create BEC with a density-dependent gauge field and show that there's a quantum phase transition that also should break this kind of symmetry D2, D4, and so on. Okay, so that remained the kind of topic we're looking into. Okay? But this is very difficult to really kind of to demonstrate a gauge symmetry. That's something we'll continue working on.
Thank you.
Chris, could you possibly put speakers on the screen up in the visible frame when
Charles, they'll show up if they have their video on. They'll show up if they have their video on, but that speaker didn't have her video on.
Okay, well then, yeah, those who are asking questions, please feel free to turn on your video so we can all, see who's talking and get some discussion going. Who'd like to ask the next question?
So we have one student that relayed a question who doesn't have a microphone. And so Monica was wondering about the pattern formation and whether you've thought about studying pattern formation with different driving fields that could lead to even more symmetry groups.
Right, that's something we're currently also working on with the case 11, the theories in our department. So one idea going beyond this the D4 and the D6 symmetry, we're trying to see whether we can create some kind of quasi-crystal. Okay. And by quasi-crystal, there are two fundamental difficulties. One is that it doesn't really form a closed loop. I guess I didn't explain this very well. You can see here, the first process, okay, look at the blue arrow, okay, that can create a pair production. The second process is given by this green arrow, okay. So what happens is this particle will go to here, the other particle will come here. Once they form this 60 degrees, they can support each other. Okay, so if you can kind of have a closed kind of a system for population to really move around, then that kind of mode can be resonantly enhanced. But for the quasi-crystal, say it's 5-fold and 8-fold, okay, there are always some kind of leakage. Okay? So we haven't figured out a very good way to get a strong and stable kind of this pattern with other symmetries. But we're still trying. We're still trying. But the other thing is that this the pattern formation is also more complicated if it turns out the system doesn't have a kind of long range kind of correlation. That will also be another difficulty to see quasi-crystal pattern in real space.
Anything else?
Can I ask a question? I'm a postdoc. I have a question related to Jay's question. So we know that this eigenstate thermalization hypothesis, and I remember there's a theoretical proposal that the entanglement entropy after quantum quench will go to the thermal entropy. So I would like to know if you have any comment on your result, because it looks like you start with some condensate, and eventually you can also have some thermal entropy. So is there a way to demonstrate such a nice relation, quantum correlation between thermal entropy?
Yes, that's something we very much like to do. I appreciate this any income. I can tell you where we are at the moment. So I show you this, we can see a temperature increases, entropy increases. These are all based on local observables. But pair production or this Unruh radiation and so on actually create some kind of entangled state between all these thermal modes. In principle, the von Neumann entropy of the whole system should remain 0. So that means the entropy we see here, okay, is that we're kind of ignoring all the correlation because we only perform kind of local measurement. So to prove kind of this entanglement in this kind of multi-mode continuous variable system is very difficult. We haven't really figured out a very good way to do it. But so far, what we can show is that if we perform the modulation in the proper way, say, for example, after, say, 20 milliseconds, okay, and then we see entropy increases by, I don't know, 1 kb, and so on. If we we want to, we can show that we can reverse the evolution if we change the modulation phase. Okay, I think this Lei also was one kind of work on this and show that we can reverse about 20% or 30% of the entropy. It's not much, okay? But once you can reverse it, it shows that some of the entropy is likely coming from entanglement. Okay? So far, that's the best we can do. And we certainly appreciate any further suggestion how to show the kind of entanglement entropy in the system.
Thank you, that's very interesting.
Okay.